Hello, I'm Bill Kinney. This is video number 30 in my series on Foundations of Arithmetic, Algebra, and Graphing. I'm going to talk fairly fast in this video because I want to try to wrap up this sub-series on decimals, real numbers, and percentages. It's part 9 of that sub-series. I'm hoping I can wrap it up in this video here. In the last video, we saw that rational numbers are pretty much all you need for practical measurement because you can measure things as accurately as you wish. However, theoretically, they're not good enough for theoretical measurement. Like if you have a triangle like this, it turns out that the hypotenuse has a length square root of 2, which is not a rational number. And I think I briefly mentioned that it's pretty easy to prove square root of 2 is not rational. I would encourage you to look it up. It's kind of a fun explanation for why it's not rational. There are plenty of other numbers that are not rational, the most famous of which is the number pi. 3.14159, blah, 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 blah. It goes on forever and ever without a repeating pattern, and in fact, not really much of a pattern at all as far as we can tell. The digits seem pretty random, though computable. That is not a rational number. It is irrational, though it is much harder to prove. Another famous one is called E. It starts out looking like it's perhaps a rational number because if you check it on your calculator, it should be in most calculators. I typed it in this calculator with an E. There was an E button. On this one, it was above my division symbol here. So it turns out to be an important number that looks like it's rational. It looks like the 1828 repeats. But if you had a calculator with more accuracy, it turns out that it doesn't repeat. Once you get past that last 1828, all of a sudden you get, I'm looking it up here, 459 comes next, and you'll see if you have technology that can show you more decimals that it's not a repeating pattern. Couple famous irrational numbers. I want to emphasize that the real numbers include all these decimals and include decimals that, have a whole number part in front of them as well, like 754.38127, blah, blah, blah. And I'm not saying whether it's got a repeating pattern or not. It includes negative numbers, negative 63.1890117, blah, blah, blah. Any number that you can imagine writing down as a decimal is included in the set of real numbers. It turns out, it's much harder to prove, but it turns out that the real numbers satisfy all the algebra properties that are important for doing algebra, for using the formulas, etc. The algebra properties are closure. You adding two real numbers, you get a real number. Associativity, commutativity, distributive property. Let me write some of these down. And what I want to do in this video is just write them down abstractly. You want to learn to recognize these properties in an abstract form if you're going to get good at algebra. The closure typically needs to be stated more as not as so much as a formula, but a statement. If x and y, if these symbols represent real numbers, which again include essentially any decimal, all the rationals and all the irrationals, then x plus y and x times y, which I'll write like this, are also real numbers. Addition, it's closed under addition and multiplication. That's much harder to prove than you might imagine, but it can be done once you've defined really what addition and multiplication mean. We won't go into that. What else can you say? There's associative property, so-called associativity. Doesn't matter where you put parentheses, it doesn't matter how you associate these numbers with respect to operations. If you've got x plus y plus z, where x, y, and z all now represent numbers. In fact, I can write it this because it doesn't like this without parentheses, because it doesn't matter whether I do x plus y first and then add z, or do y plus z first and then add x. Same thing with multiplication. Do x times y then times z. It's the same as first doing y times z, indicated by those parentheses there, and then multiplying by x. Commutative. X plus y is the same as y plus x. X times y is the same as y times x. Distributive. X times y plus z is the same as x times y plus x times z. Order of operations is fundamental here. Over here on the left, you're saying, because of the parentheses, do the y plus z first, and then multiply by x. Over here, you're saying, do these two multiplications first. First, find x times y, and also find x times z, and then add the results. And the distributive property says you get the same thing. You should check these out with your calculator, trying different numbers in for x, y, and z, and seeing that these do seem to work. Subtraction is not commutative, for example. Is there a way we can verify that algebraically? Well, just an example is good enough, actually. 5 minus 3 is 2, which is not equal to 3 minus 5, which is negative 2. But is there a problem with that as far as subtraction being thought of as adding the negative? No, there's not. It doesn't disprove the commutative property for addition, because when you do 5 minus 3, that's 5 plus negative 3. That's really different than doing 3 minus 5. 3 minus 5 is really 3 plus negative 5. The negative sign is on the other thing. 5 plus 3 is, by the commutative property, equal to 3 plus negative 3 plus 5, and 3 plus negative 5 by the commutative property is equal to negative 5 plus 3, but those are not the same thing. You're not doing the negative sign by the same number in those things. This one's got the negative sign in front of the 3, this one's got it in front of the 5. So subtraction is not commutative. In general, x minus y does not equal y minus x, unless x and y happen to be the same, so that both of these differences are 0. Though in general you can say that x minus y does equal negative 1 times y minus x, and that can be verified by the distributive property. Multiply the negative 1 through, and then simplify. That's the same as x minus y. So just a quick summary, that the real numbers do satisfy some abstract properties, and these are important for doing algebra and solving problems, so they are worth thinking about and learning. Subtraction doesn't satisfy some of them. For example, it doesn't satisfy the commutative property, and division doesn't either. Think about examples. That's going to be the end of this particular video series, though we will certainly use these ideas on decimals, real numbers, and percentages in other future sub-series.